Today we will discuss the definition of Cartesian product or direct product. So the definition is, let A and B any two groups. We defined the Cartesian product of A and B is denoted by G is equal to A cross B, which is equal to A comma B, such that A belongs to A and B belongs to capital B. We defined product in G as A1 comma B1 A2 comma V2 is equal to A1 A2 comma B1 V2, which belongs to G. Equation number 1. Show the Cartesian product is a group. A Cartesian product of two group in a group. Let A1 comma B1 comma A2 comma B2 comma A3 comma B3 belongs to G. So by the closure property, A1 B1 comma A2 B2, which is equal to A1 A2 comma B1 B2 belongs to G by equation number 1. Now the associative property, A1 B1, so A2 comma B2 and A3 comma B3, which can be written as A1 comma B1 and A2 A3 comma B2 B3 by first property. So A1 A2 A3 comma B1 B2 B3, then A1 A2 A3 comma B1 comma B2 B3. Since A1 comma A2 comma A3 belongs to A, so by associative property, A1 A2 comma B1 B2 A3 comma B3, so A1 B1 A2 B2 and A3 B3. Now the third property is identity property. If E is the identity element of A, if E is the identity element of A and F is identity of B, now A1 B1 E comma F is equal to A E B F, which is equal to A1 B1. So E comma F A1 B1 is equal to A1 comma B1. Hence E comma F is identity element of G. Now the inverse property. If A1 comma B1 belongs to G, then A1 belongs to A and B1 belongs to B. Since A and B are group, so A inverse belongs to A and B1 inverse belongs to B. Then A1 inverse comma B1 inverse belongs to G. Hence A1 comma B1 A1 inverse comma B1 inverse, which is equal to A1 A1 inverse comma B1 B1 inverse, which is equal to E comma F. Similarly, A1 inverse comma B1 inverse A1 B1 is equal to E comma F. So A1 inverse comma B1 inverse is the inverse of A1 comma B1. Hence G is a group. Now there is a theorem. If A is a group, G is equal to A cross B, then A bar is equal to A comma F, such that A belongs to small a belongs to A is a subset of G. Then A bar is isomorphic to A and is normal subgroup of G. Proof है इसका. First condition, A bar is a subgroup. So let A1 comma F and A2 comma F belongs to A bar, where A1 comma A2 belongs to A. Now A1 comma F and A2 comma F is equal to A1 A2 comma F F by 1. So A1 A2 comma F belongs to A bar. So F is identity of B, which is equal to A1 F A2 F belongs to A bar. Since A bar satisfy the closure property, inverse property है, if A comma F belongs to A bar when small a belongs to A and A inverse belongs to A, then A inverse comma F belongs to A bar. Now A comma F A inverse comma F, which is equal to A inverse comma F F, so E F. Hence inverse property is satisfied since A inverse F and A1 F is equal to E comma F. A bar is a subgroup of G. Second condition है, A bar is a normal subgroup of G. let a1 comma b belongs to g and a comma f belongs to a bar, then a1 b1 a1 f a1 comma b1 inverse. So a1 b1 a1 f a1 inverse b1 inverse, which is equal to a1 a and b1 f. So a1 inverse and b1 inverse, which is equal to a1 a inverse comma b1 f b inverse, a1 a inverse comma ef. So a1 a inverse comma f, which is belongs to a bar, then a bar is a normal subgroup of G. Third is a bar is a isomorphic to a. Define a mapping phi such that a tends to a bar by phi a is equal to a1 f. So सबसे पहले देखते हैं phi is 1 1. If phi a is equal to phi b, then a1 f is equal to b1 f, which is equal to a equal to b, so f equal to f. Now a is equal to b, thus phi is 1 1. Now phi is onto, phi is obvious onto is that for every a1 f belongs to a bar, there is a unique a comma a belongs to e such that a belongs to f, such that phi a is equal to a1 f, hence phi is onto. Now the third is phi is homomorphism. If phi a is equal to a1 f and phi b is equal to b1 f, then phi a1 b is equal to phi, a1 b comma f, which is equal to a comma f and b comma f. So phi a dot phi b, phi is isomorphic to a bar, so phi is homomorphism. Now the another definition is internal direct product. If G is equal to n1 cross n2 cross n3 and uh, so on cross nn, where n1 comma n2 comma so on nn are normal subgroup of G, and if G satisfied two condition, first G is equal to n1 comma n2 to so on nn, given G small g belongs to G, then G is equal to m1 m2 and so on mn, such that mi belongs to ni, then we say that G is an internal direct product of n1 comma n2 comma so on nn. Now there's a theorem. Suppose that G is internal direct product of n1, n2 and so on nn, then for I does not equal to j, ni intersection nj is equal to e, and if a belongs to ni, b belongs to nj, then ab is equal to ba. इसका प्रूफ है let x belongs to ni intersection nj, then x belongs to ni and x belongs to nj. If x belongs to ni, then we can write x as x is equal to ei and so on ei minus 1 cross e I plus 1 and so on ej is so on en, where e f is equal to e, but every element and so in particular x has unique representation in the form m1 m2 and so on, where mi belongs to ni. Therefore the two decomposition in this form, x must conclude the entry from ni in each must be equal. In our first decomposition, this entry is x in the order if ei is equal to e. Hence x is equal to e. Thus ni intersection nj is equal to e for I is not equal to j. Suppose that a belongs to ni and b belongs to ni, and I is not equal to j, then a inverse belongs to nj, comma a belongs to ni is a subset of G, then a belongs to G. Since ni is normal, now b is equal to nj, so it implies that b inverse belongs to nj. Now a inverse b inverse belongs to ni. Similarly, b belongs to ni is a subset of G, so b belongs to G and a belongs to ni. A inverse belongs to ni and I is normal in G. So a inverse b inverse belongs to ni. Also a inverse b inverse belongs to ni, but then A inverse B inverse belongs to Ni intersection Nj, which is equal to E. So A inverse B inverse, which is equal to E. A inverse is equal to E. So A का whole inverse BA is equal to E dot BA, which is equal to AB dot E is equal to BA. Hence proved.